Alright, so now we look at section 4.7, which deals with row space, column space, and null space. Right, so recall that for an n by n matrix, A, given with those entries, the following vectors denote the row vectors, right? So it's the rows, the vector formed by taking the rows. These are vectors in Rn, okay, because they're n components, and it's an Rn because the entries of the matrix A are all real numbers. Right, so those are the row vectors of A. And again, the column vectors are just the vectors formed by taking the columns of the matrix A. Okay, now these column vectors, there are n such columns, and each column vector is an Rm because there are m rows. All right. And as I said previously, we call these column vectors. All right, now just to formalize the following, if A is an n by n matrix, then the subspace in Rn that is spanned by the row vectors of the matrix A, so you take the matrix A and you take these row vectors, right? Now the space spanned by those row vectors, in other words, what's the space spanned by those row vectors? It's a space where each vector is a linear combination of those row vectors. Okay, and we call that the row space of the matrix A. And in the subspace Rm, the space spanned by the column vectors of A, that's called the column space of A. So going back again, if you look at these column vectors, C1, C2 up until Cn, and you look at all possible linear combinations of these column vectors, then that space, you're looking at the set that contains all the possible linear combinations of those column vectors. That is the space spanned by those column vectors, and we call that the column space of A. Then lastly, the solution space of the homogeneous system of equations derived from the matrix A, which happens to be a subspace. Remember, we established that it's a subspace because if you take any two solutions to the homogeneous linear system, then if you sum the two together and you look at that, that is obviously going to be a x bar plus a y bar, and that's just going to be the zero vector. And also for any scalar multiple of a solution, there's also going to be a solution to the homogeneous linear system. Right, so that is according to our vector algebra, and that is just the zero vector. So the null space is always a subspace, and it's a subspace of Rn, right, because there are n columns, and therefore it's an Rn, and therefore that is called the null space of A. So the null space of A is just all the set or the space formed by all the possible solutions to that homogeneous linear system. Alright, so let's do our first example. They ask us to distinguish between the row space, column space, and null space. So there we're given a matrix and we are asked to find the row space, the column space, and the null space. So what is the row space? Alright, so there we've got our first row. Alright, oh my God, yes. Right, there we've got our second row. Right, so what is the row space? The row space is the span of the two row vectors. There's my first row vector. Right, there's my second row vector. Okay, so that is my row space. What is my column space? Right, so get the column vectors there. There are my column vectors, C1, C2, and C3. Okay, now the column space then becomes, we'll denote the column space by C. It is the span of the column vectors. Right, so there's my first column vector, second column vector, right, third column vector. Right, so that's my column space and my row space respectively. So what is the null space? Right, so we need to find the solution to that linear system. Okay, so we take the matrix A, and we've got our variables. It's a 3x1 matrix. Right, so there's our 0 matrix. Right, and from there we've got, and there we're given our two equations. Right, using parameterization, we can set z as a fixed real number. Then we can solve for y and z as minus t. And so the null space becomes, okay, so the null space is all vectors of that form there. Right, so we'll call it the null space. N is the set of the solution space. So it's all vectors of that form where t is a real number. Alright, so that is the null space. Alright, so next we have, recall that if we take the matrix A and we multiply it with a column vector, and we go and multiply this row with that column, this row with that column there, carry that process through and multiply that row with that column there, and that can be expressed as this linear combination, that linear combination, where in fact we have the column vectors of A, and we're writing a linear combination of the column vectors of A down. So it turns out that A times x, where x is a column vector, can be represented as a linear combination of the column vectors of the matrix A. Now that's easy to verify that. It's just applying the normal matrix products operations. That brings us to this theorem here, which is a direct consequence of this observation. If you have a system of linear equations that correspond to that system Ax equals b, then we say that is consistent if and only if the vector b is in fact in the column space of A. Right. So if we take that b, that column vector, we want b to be equal to Ax. In other words, essentially what we want is we want this vector b, which is that column vector, we want that to be equal to that. In other words, it's the same as saying that b is in the column space of A. B is in the column space of A because we need to be able to write b as a linear combination of the column vectors of A. And that's the same as saying we can find an x1, x2 up until xn such that b is a linear combination of the column vectors of A. So that's all equivalent. It's basically equivalent to saying that if this is consistent only if and only if b can be expressed as a linear combination of the column vectors of A. In other words, that's the same as saying that I can find values for x1, x2 up until xn, and that's the same as saying that AX equals B is consistent. Right, so the next example is here they ask us to show that A and the vector B given. We are asked to show that B is in the column space of A, and we are asked to write B as a linear combination of the columns of A. So all they're actually asking us is when we need to look at the solution of the system AX equals B. Alright, so AX equals B translates into, right, so that becomes my linear system I need to solve, and that can easily be done. From that we get a system of three equations. Okay, from that we can solve our linear system as, right, so we can solve for x is -1, z is 2, and y is -3. Right, so there's my first column vector. Right, there's my second column vector. Right, there's my third column vector. And there we've got our values, -1. Right, so there we've got our second value, -3. And our third value, 2. And we get our linear combination. So we've just shown that the vector 1, -1, 0 is a linear combination of the column vectors of my matrix A, and we've expressed it as a linear combination. Right, that brings us to Theorem 2, or Theorem 4.7.3. Elementary row operations do not change the null space of a matrix. Right, so if you have linear systems, you get a linear system from your from this equation here, and you have set up a linear system. That's a homogeneous linear system. And if you apply row operations to A, it is most certainly not going to influence the answers that you get to, because essentially to get to the answers you have to reduce A into its reduced row echelon form, and the null, that's not going to change the null space. Right, the second one, elementary row operations do not change the row space of a matrix either. Right, so let's see why that is the case. I'm not going to write out a proof, but I'm just going to illustrate it with an example. Right, so let us take that matrix, n by n matrix, and let's look at the row space. The row space is just a linear combination of the row vectors of A. Let's take a vector v and write it as a linear combination of the row vectors, and R1 denotes the first row, R2 denotes the second row, up until the mth row. Okay. There's a linear combination of the row vectors of A, and V is obviously in the row space of A. Now let's take, for argument's sake, let's do one row reduction on A. Let's take 3 times the second row plus the first row. So I'm going to change the first row by taking 3 times the second row and adding it to the first row. So there's my operation. Alright, now doing that, that's going to give me a new matrix. It's going to give me a new matrix that's going to have a different first row. Right, so let's call this new matrix A prime, and you can see the A prime has got a new first row, and the new first row is that row there. Okay, all the other rows still stay the same. Let's go back to the vector v. So we can take the first row of A, we can add 3 times the second row, and we can subtract 3 times the second row. So I've not really essentially done anything, and that becomes then. All right, then just regrouping the term, you can see that term becomes the new row R1 prime, and we keep the R2 and all the other rows the same. So this is going to be a new coefficient. Right. Now, we go back to this matrix here, A prime, right? And we go back to the vector V. We said the vector V is that linear combination, right? So what does this mean? It means that the vector V bar is still in the row space of the new matrix A prime, because it's a linear combination of the row vectors. Now, I've only done one operation. You can do any number of row reductions that you want. The vector that you choose originally that's in the row space of my original matrix A, that vector is not going to change. It's going to be in the row space of any number of row reductions. Right, so the matrix that you form by repeatedly reducing A, the vector V is going to be in the row space of that reduced matrix as well, in the rows of that reduced matrix. All right, so that brings us to Theorem 4, which says that if A and B are row equivalent matrices, then number one, a given set of columns of A is linearly independent if and only if the corresponding columns of the matrix B are linearly independent, right? And given a set of column vectors of A, if the given column vectors of A forms a basis of the column space of A, that happens if and only if the corresponding column vectors of B form a basis for the column space of B. Right, so I want to just look again at the first point. Why is it that if you have a linear independent columns in A, why is it then that those same corresponding columns in B will also be linearly independent and vice versa? Well, it's a very similar argument to the one I used to explain Theorem 3. Right, so let's take my matrix A again. And again, we're not proving the theorem, we're just using an example to illustrate it. All right, so let's say my first two columns are linearly independent. So let's take first column, and there's my second column vector formed by my second column. So we assume that these two column vectors are linearly independent. So write that formula down. We know that the only solutions to the k's is the trivial solution. That is where k1 is equal to k2 is equal to 0. All right, let's go back to the previous example. So let's just use one row reduction. We change the first row by adding 3 times the second row to it to form a new matrix. It's going to have a different first row than A does. And let's call this matrix A prime. Okay, so there's my matrix A prime. And it differs only in the first row because that's the row reduction I did to change it. Okay, so that is my, we take that separately, and what we want to do is we want to answer the following question. Like, we want to show that the first column and the second column of A prime are linearly independent. I take my first column vector. I take my second column vector there. Okay. Right, and write the 0 vector is a linear combination between those two column vectors. Let's call it C1 and C2. Okay, now we want to show that C1 must be 0 and C2 must be 0. Recall that A11 prime is the first entry, first row in the first column, plus 3 times the entry in the second row in the first column. And A12 prime is the is the entry in the first row and the second column plus 3 times the entry in the second row and the second column. Right, so take it separately and replace the first row of each of the column vectors. All right, so from this equation we have that C1 times that plus C2 times that is equal to 0. Right. Okay, so then we can write that matrix equation. We can write it in this form here. Okay. Right, so now the question is, what happens to these terms? What happens to these terms? We know that C1A21 plus C2A22, there's C1A21 plus C2A22 is 0. So this matrix plus that matrix is going to be the 0 matrix. All right, so the moral of the story is those yellow parts, like I said, are going to fall away. Okay, and we're going to be left with that. But this is the column, first column of the matrix A, and that's the second column of the matrix A. And we assume that these two columns are linearly independent. So that is literally going to force C1 to be equal to C2 to be equal to 0. So what have we seen here? What is the main thing that we can get from this? Is that if you, as in this example, we assume the first two columns of the matrix A, they're linearly independent, and then we changed a row. We added 3 times the second row to the first row, and we formed a new matrix, and we showed that the first two columns of the new matrix is also going to be linearly independent, and vice versa. Right, so if you can do it for any two row equivalent matrices A and B. If you go from A to B, and A has columns that are linearly independent, then B, the corresponding columns of B is going to be linearly independent, and vice versa. If you have linearly independent columns in B, then their corresponding counterparts in the matrix A are also going to be linearly independent. Right, so the second part, if we're given a set of column vectors of the matrix A, and that set forms a basis for the column space of A, that happens if and only if the corresponding column vectors of B also forms a basis for the column space of B. Right, so you can't have one without the other. That's if A is and A and B are row equivalent. So again, I'm not going to prove this, but I'm going to just illustrate this quickly with an example. We're going to use the example we used in the illustration for Theorem 4, the first part. All right, so there we've got our matrix A, and let's just assume for argument's sake that the first two columns of the matrix A forms a basis for the column space of A, and we call it B subscript C. The basis for the column space of A it's those two vectors. So let's assume for argument's sake, as an illustration, that the first two columns of A forms a basis for the column space. All right, and there's our matrix B. And we obtained B from A by applying this row reduction. We took we changed the first row by adding 3 times the second row of A to the first row of A, and that created a new matrix B, which is row equivalent to A. Now my aim is to now show that the first two columns of B forms a basis for the column space of the matrix B. Right, now we remember when we illustrated with an example the first part of Theorem 4. In other words, if you have a set of column vectors and those column vectors of A are linearly independent, then the corresponding column vectors for the matrix B are also going to be linearly independent. Now what this means is that because this is set as a basis for a column space of A, it means those two vectors, this one and that one, is going to be linearly independent. Now that is going to imply that in my matrix B, the first two column vectors are going to be linearly independent. Right, so therefore by the first part of Theorem 4, because the first two columns of the matrix A, those column vectors are linearly independent, it means the first two column vectors of B is linearly independent. So now I just need to show that this set here is a basis, so I just have to make sure the spanning property holds. Alright, so let's pick a vector V. Let's pick a vector V to be in the column space of B. In other words, it is a linear combination of the column vectors of B. Alright, and just for argument's sake, V is just, again, it's just some column vector, right? Alright, so now what I want to do is I want to go back to the matrix A. So I want to reverse this operation to go back to the column vectors of A. Alright, so I'm interested in the first row of that matrix equation. So there we take V1 is clearly equal to C1 times that, C2 times that, up until there, right? And we get it from that part there. Now, the operation I used to get the first row of the matrix B, recall that operation? Right, it was the operation, I took the first row of A, I changed it by adding 3 times the second row of A. Right, so doing the replacement, we get the new vector, well, the same vector V1, but we replaced these terms. Remember, we get A11 prime by taking 3 times the entry in the second row in the first column and adding it to that, and we get the subsequent entries as well. Right, so in my original matrix equation, I do the substitution in the first row and get the following. Right, so there we get the substitution. Alright, so again, V1 is equal to this whole term, that term there. And from there we can get... Right, so we get that there, okay, and plugging all that back into the matrix equation, we get that new matrix equation where the quantity V prime is, where the quantity V prime is this whole quantity, right? So it's that whole quantity there. Alright, so also observe that we can do another substitution. V2 is equal to C1A21 plus C2A22 up until CNA2N. Right, so then we get that quantity there. So you can see that corresponds to that term there, that term corresponds to that term there. Up until there, that term corresponds to that term there. Alright, so from there we get that V prime is V prime is V1 minus 3V2. So we get that expression there for this vector here. Now please note that this vector, which is that vector there, is in the column space of the matrix A, because it's a linear combination of the columns of the matrix A. Now we said in the beginning that the two columns of A, first two columns, forms a basis for the column space of A. Therefore, because this vector is in the column space of A, it means that it is spanned by the basis column vectors of the matrix A. Thus, if I take that vector is a linear combination of the two columns of the first two columns of the matrix A. There are the first two columns of the matrix A. Right, so we can find two scalars K1 and K2 such that this vector is a linear combination of those two column vectors. All right, note that we can write V2 as K1A21 plus K2A22. Right, doing the substitution, we plug the V2 in there, and we get this whole vector. All right, rearranging the terms, we get the matrix equation, and what that then becomes is, right, so there we've got our matrix equation, and what is that now? All right, so there we've got a linear combination. Now, please observe the following, right? This vector is the vector that I originally chose to be in the column space of the matrix B. Okay? These two vectors are the first two columns of the matrix B. So I've just shown that this vector lies in the span of the first two column vectors of the matrix B. So therefore, what am I saying? Because we assume the first two column vectors of A is a basis for the column space of A, we can now also say that the first two columns of the matrix B is a basis for the column space of the matrix B. Now again, this is just an example. This is not a proof. So we just merely looked at one row reduction. All right, that brings us to the very important theorem, Theorem 5. Theorem 5 is, using everything we've done up until now, if we take the matrix A and we keep reducing it until we get the reduced row echelon form R. So remember that R and A are row equivalent. Because I can go from A to R using row reductions, and I can go from R to A using row reductions, reversing those row reductions. Now, the row vectors of R with the leading ones form a basis for the row space of A. Okay? And the column vectors of R with the leading ones identify the column vectors of A that form a basis for the column space of A. Okay, so if we look at the column vectors of the matrix R, and we look at the columns that contain the leading ones, they will form a basis for the column space of the matrix R. And by the previous theorem, because R and A are row equivalent, the columns that correspond to the ones with the leading ones in R, those columns in A are going to form the basis for the column space of A. Okay, so I just want to illustrate Theorem 5, the first part of Theorem 5, quickly with another example. All right, so just to illustrate it again, go back to our previous example. You take the matrix A and you take a vector V that's in the row space of A. So there's a vector v. Take a vector v in the row space of A. All right, and now take that reduced row echelon form matrix R. So I've just taken A and I've just repeatedly operated using row reductions, and I've gotten to my matrix R. Now remember, the matrix R has got possibly 0 rows, and it's got rows that have only leading ones. Now the 0 rows are not going to play a role. It's only the rows with leading ones. Now remember, we said that if we repeatedly manipulate the rows of A using row reductions, we said that this vector V, for every row reduction that you do to A, the vector V is going to be in the row space of that reduced matrix. So for every matrix that I get from A by applying a row reduction or multiple row reductions, V is still going to be in the row space of that new matrix that I obtained by doing the row reductions on A. Right, so V is going to be in the row space of R. And the only row vectors there are, well, the ones that matter are the ones with the leading ones, because all the other rows are going to be 0 rows. So therefore, the basis for my row space of A can be obtained by just reducing A to R and then taking the vectors with leading ones. All right, that leaves us with the following remarks. Essentially, one can reduce a matrix to row echelon form and then pick the rows with leading ones from R, and that will be a basis for the row space. That's an application of the previous theorem. And then pick the columns of A corresponding to the leading ones in R as a basis for the column space of A. Right, now the rows must be taken from R, and the columns from A. Now, if we want to use the rows of A to find a basis, we can row reduce the transpose of the matrix and then select appropriate columns from the transpose of A. And hence, essentially, that means I'm choosing rows from A. Let's look at an example. All right, so find a basis for the row space and the column space of the matrix A. Okay, so there's the matrix A, and what we're going to do is we're going to find a basis for the row space, and we're going to do that by row reduction. We're going to change the first row by adding the second row to it. All right, so we get the next matrix, and then what we're going to do is we're going to change the third row by adding the second row to the third row. Right, so we get our second row reduction. Okay, the next row reduction, what we're going to do is we're going to take the third row and multiply through by -1, and we're going to take the second row and multiply through by -1. All right, and lastly, we're just going to rearrange the rows as follows. All right, so we get the last matrix there, and the leading ones, they occur in the first row and the second row. So our basis for my row space will become the following. Right, so we take our first vector there. And then we take our second row with the leading one. So the basis for my row space will be the set containing the two leading one row vectors. Right, so what will be the basis for my column space? Now, the columns with the leading ones are is the first and the second column. Okay, so remember what we said. How we find the basis for the column space is now we need to go back to my original matrix and basically select the first column and the second column. So therefore the basis for my column space, let's call that B for BC. Right, so there you've got the first column vector, and you've got the second column vector, and that is going to be my basis for my column space. All right. Okay, so the next problem they ask us, find the basis for the row space of A in terms of the rows of A. So we need to use the rows of A to specifically find a basis for the row space of A. Now, we don't want to go and reduce the matrix A and find a basis that way. We actually want to physically use the rows of A. So what we're going to do is we're going to use the transpose of the matrix A. Alright, so there we've got the matrix A, and let's look at the transpose. There's the transpose. Now we want to find the space that's spanned by the actual column vectors, right? And how we do that is by reducing the transpose of the matrix A. Alright, so I'm going to start reducing the matrix, the transpose of A, and I'm first going to do that by taking -2 the first row and adding it to the second row. So I'm changing the second row. Alright, so there we've got our first reduction, and now I'm going to change the second row by multiplying the second row with -1. Alright, so we get that, and then what I'm going to do is I'm going to add negative the second row to the third row and get the last iteration. Okay, and that gives me... Okay, now if we investigate the columns with the leading ones are the first one column and the last column. It's got a leading one in it. Alright, so we need to now go back to my original transpose matrix. Right, so there we've got our transpose, and go and look at the columns that correspond to the transpose, the one with the leading ones. So it is going to be the first column, and it is going to be the last column. So therefore a basis for the row space becomes the following. Right, there we go. Here's my first vector. We took the column 1, 2, 0 and we took its transpose. And then we took the third column and we took its transpose. So there is an alternative basis for the row space of the matrix A using the transpose. Alright, so to recap the procedure for finding the basis for row, column and the null space of A, you take the matrix A and you find the row echelon form R of A. Now for the basis for the row space of A, you go and look at the rows with the leading ones, and those rows with the leading ones, the leading one rows you gather them together, and that will be a basis for the row space of my matrix A. Right, for the column space of A, you go to the row echelon form of A, and you go and look at the columns containing the leading ones. Right, those columns with the leading ones, you go back to your matrix A and you look at the columns that correspond to the columns of R with the leading ones. And those corresponding columns of A, that's going to form your basis for your row space of A. Now for the null space of A, you basically solve this system, right, by reducing the matrix A to its row echelon form, and then you retain the vectors once the parameters have been extracted. Alright, so physically you solve the system. And whatever your solution is, that is your null space. Alright, so in this example, they ask us to find the basis for the row space, column space, and the null space of this matrix A. Okay, so there's my matrix, and what I'm going to do is I'm going to change the second row by taking the first row and adding it to the second row. Alright, then I'm going to change the last row by taking negative a half and multiplying that with the second row and adding it to the last row. Right, so then lastly I'm going to create leading ones and get. Alright, so there I get my reduced row echelon form of my original matrix A. So now the basis for the row space is going to be, basis for the row space, BR, is going to be the vector 1, 2, and 0, 1. Right, for the basis for the column space, we look at the columns with the leading ones. That column has got a leading 1, and that column has got a leading 1. And then we go back to my original matrix and look at the columns with the leading ones. Right, so there's my column basis for my column space. And then my null space, we need to find the null space first. Alright, so there we set up our matrix equation, and from that we can set up 3 equations that we can solve. Alright, so there we get our 3 equations, and from there we get the null space, which only contains the 0 vector. So it follows that the null space it has a 0 dimension, so it doesn't have a basis. Alright, so here they ask us to find the basis for the span of the following vectors and express the remaining vectors as a linear combination of these basis vectors. Right, so we're given the vector set S, and it lies in P2, and we are asked to find a basis for the span of the vector set S. Alright, so instead of doing it the normal way, we're going to use this section to make this problem a little bit easier, instead of doing all of that work we used to do to prove this type of problem. So taking the first vector in S, we see there that we can represent x in that form. Now remember, P2 is the set of all polynomials of degree at most 2. Now note that these coefficients correspond to a column vector, and the column vector is that column vector. Right, so the second vector, we can express in this form. And that corresponds to another column vector. And that is the column vector that it corresponds to. Alright, so 2 minus x can be expressed as in that linear combination. And that corresponds to another column vector, which is the last vector is expressible in that linear combination, and that corresponds to another column vector. Okay, so those are 4 column vectors. Now, essentially what I want is, I want to find the span of these, I want the space spanned by these column vectors. So I'm going to construct a matrix from these columns, and then I actually want to find I want to find the span of I want to find the column space of this matrix. Alright, so there are my 4 column vectors, and now I construct a matrix as follows. Right, so there's my first column of my matrix. Alright, there's my second column of my matrix. Alright, there's my third column of my matrix. And my last column is the last column that I obtained, corresponding to the last vector in S. Alright, so there we've got our matrix A, and what we want to do is we want to find a basis for the space that is spanned by these column vectors. So we're asking for a basis of the column space of the matrix A. Okay, that is what we are interested in. Right, so taking our matrix A, we will write A in row echelon form. So we do that first by interchanging the first and the second row of the matrix A. Then changing the third row by taking -1 times the second row and adding it to the third row, we get right, okay. Then taking the last row and creating a leading one by multiplying through with -1/2, we get okay, and then going further than that, we get okay, so now upon investigating the final matrix, we look at the columns that contain the leading ones. And that's a column that contains a leading one, that's a column that contains a leading one, and that column contains a leading one. Going back to my original matrix there, we see that column, this column here corresponds to that column there, this column here corresponds to that column there, this column here corresponds to that column there. So therefore, the basis vectors for my column space of A become, okay, so there my basis for my column space of A is going to be, right, there's my first vector, right, there's my second vector, and there's my third vector. So there's my completed basis for my column space of my matrix A. Right, so to complete the problem there we've got the basis, and that corresponds to the functions. Right, there's this vector corresponds to the function. right, the second column vector corresponds to. Right, there we have it. That corresponds to. Right, so there we've got our third column vector, and that corresponds to the function. Okay, so the basis for the space spanned by the vectors in S is. There we've got the basis for the space spanned by S, and writing the other vector in S as a linear combination of the others, we get. Alright, so there we've got the linear combination. 1 times x plus 1 times 1 plus x squared plus 0 times 2 minus x is 1 plus x squared. Alright, so just take note that we can extend the equivalence theorem to properties 7, 8, 9, 10, 11, 12, and 13. Remember, the determinant of a matrix A determines whether it's invertible or not. If its determinant is not 0, it means it's invertible, and therefore this, we know, has only the trivial solution. In other words, first of all, the 0 matrix is in the column space of the matrix A, and the only solution there is the trivial solution for x. Therefore, that's going to imply that these column vectors of A are going to be linearly independent. And therefore, because they are linearly independent, they're also going to span Rn. And the column vectors of A also forms, then obviously going to be a basis for Rn. Now, the row vectors of A are going to be linearly independent, because if A is invertible, the reduced row echelon form of A is the identity matrix. And because A and the identity matrix, they are row equivalent, and because the rows of the identity matrix are linearly independent, it means by all the theorems we've done previously in this section, it means A is going to inherit that same property. In other words, all the rows of A are going to be linearly independent. And therefore the row vectors will also span Rn, and also the row vectors of A will form a basis for Rn. And those are the extensions to the equivalence theorem.